This video is about when you are given initial change and equilibrium conditions in one single question. We call it the icebox questions. You should already be able to construct a mass action expression, manipulate those expressions to calculate them, and by the end of the video, you should also be able to use reaction quotients to determine if a system is at equilibrium, and if it's not, use iceboxes to calculate its equilibrium conditions. So the question of the video is back to the phosgene gas. If you have those same conditions of phosgene, except for you have 1 molar of CO, 2.5 of chlorine, and 1.0 molar of COCl2, identified by maybe environmental chemists who took a contaminated polluted sample, which way will the reaction proceed? Will it make more carbon monoxide or more phosgene gas? So the reaction quotient will help you figure this out. To calculate a reaction quotient, you substitute the initial conditions into the same mass action expression we've been practicing. This gives you the ratio, but it's not at equilibrium, and we can use it to compare to the equilibrium. So K and Q are found the same way, products or reactants. If the K equals the Q that you are given, it's at equilibrium. If the Q is too many, it means that it made too many products. It's much more product favored than it should be, and it shifts left or reverse to make reactants. If the Q is much smaller than it should be, that means it has too many reactants, it's too far reactant heavy, and it shifts right to restore and make more products and use up those reactants. This is a good slide to make sure you jot down. So here's an example of how we'll use it. The Kc was given at 54.3, shows it's product heavy, but we want to know if we are in fact product heavy in this reaction. So we have 0.243 moles of hydrogen and 0.0146 moles of iodine, which shows a very small amount of reactants, and 1.98 moles of hydrogen and iodine. So it seems product heavy, but we want to know if it's enough. And they're placed in a 1 liter container, which is important because remember Kc's can only be concentrations, so that changes all these moles into molarities. Which way will it shift to achieve equilibrium? So what we're going to set up is our products or reactants, which is Hi squared over H2 times I2, and plug the numbers in. When we calculate it, we get a Q that's 1,110. So yeah, we had a lot more products, and we had actually too many more products. So the reaction will shift left to make more reactants. So again, it's important that you know that Q is calculated the same way as K, and we just use it to compare to K. And then the second equation that we're going to talk about in more detail is icebox. After you know which way it's going to shift, you should use that shift to figure out what you will be at equilibrium. So you're only using the icebox if you're given initial conditions like a Q, but you need equilibrium conditions like a K. And so the old exam used to have question 1 on every part 2 to be an icebox. If you're looking at anything before 2014, number 1 will be an icebox question if you're looking for examples. Otherwise, anything after 2014, it's kind of mixed in the test. It will definitely be there. So here's an example. The initial conditions of A is 0.85, and they want the final conditions of A and B. So notice this is an icebox question because you have initial conditions, but they want equilibrium questions. So there's a change between I, C, E. And they gave you the Kc. So step 1 is to write the Kc out, which would be B over A, and step 2 would be to construct an icebox. The way we do that is we rewrite your equation with A and B on the top of the chart. Initial conditions go in the first box, so that what was given from the question. It was 0.85 A's and there were no B's. The changes are found by either common sense or by doing a Q. In this case, common sense, because for the fact that we have A's but we have no B's, and equilibrium has to have a little bit of both, we have to shift to the right to make some B. And then the E is just a combination of I and C. So I just kind of combined I, 0.85, minus the C, minus X, and I just rewrote it as equilibrium. I for B was 0, C was plus X, so 0 plus X is just X. We're going to plug those numbers into the Kc. So the B was X, so that goes on the numerator, and the A was 0.85 minus X, that goes in the denominator. And we got Kc from the previous slide. When we cross multiply, remember to distribute through the 0.85 minus X, we finally get an X value of 0.816 molar. So if we want to know what the concentrations are, we just plug them back into the equilibrium expression. So the X or B is 0.816 molar, and the A is 0.85 minus that X, so 0.85 minus that X is 0.034 molar. And this shows that it's product heavy, which we knew because Kc was higher than 1, and it shows us exactly how many there will be at equilibrium. Let's try another example. A mixture of 0.5 moles of hydrogen and 0.5 moles of iodine are placed in a 1 liter flask. It makes some molarities at 430 degrees Celsius. If this Kc is 54.3 and this is the reaction, let's calculate all the concentrations at equilibrium. So again, I just used the equation that was given on the top, so H2I2HI. I put the initial conditions in, so 0.5 of H, 0.5 of I, and since HI was not expressed in the equation, I put 0. I have to shift to the right because there was no HI present. Notice I subtracted 1x for hydrogen and 1x for iodine, but I added 2 x's for HI. It's not because these have to sum up. It's because there is only one H in the equation, there's only one iodine in the equation, and there are 2 moles of HI in the equation. So these are in mole ratio to each other, how they react. And then I just sum them up for equilibrium. Next, I'll plug those into my K expression, which is, oh, that came up early by accident. Products, which is HI, squared, because there's 2 of them, divided by H2 times I2. The Kc was given at 54.3, so I just plug my numbers in. HI is 2x, remember the square, and each H and I are both 0.5 minus x. A key thing is, since they're the same, I can write that as a square. And that means this type of question, I can square root both sides and make it simplified, because otherwise I'm going to have to do a FOIL in order to get 0.5 minus x squared to come out to be x alone, right? So to evade the foiling, I'm square rooting 54.3, and I square root this side to get just 2x and 0.5x once, right? Then I can just cross multiply and find the x value of 0.393. So we'll be practicing this first type quite a bit in class. Once you get your x, you plug it back in. So 0.5 minus x is 0.5 minus x is 0.107 for both H2 and I2. And 2 times x, or 2 times 0.393, is 0.786. So now I know exactly how much I have at equilibrium, where it's going to settle. Now we're going to try the example one more time, but with an additional initial concentration of 0.04 of HI. So now what we see is there's some H, there's some I, and there's some HI already present. We want to know if we're going to make more or less than we did before. I'm going to still say that shift is to the right, because remember we said that the K value was 54.3, which means there should be more products than reactants, and currently we don't have that. So if we know that, we know we're going to make more products, and then equal it out. We're going to plug that into our Kc expression, which was 50.3. I have 0.04 plus 2x squared, because there's 2 of them in the equation, and then 0.5 minus x squared because it happens twice in the icebox. I can square root both sides and solve for x, and then plug the x back into my equation. What you'll notice is, because HI is present, we make a little less than we thought we did before. So HI is only 0.82 molar, whereas in the previous slide, HI was 0.786. So a little bit more products. And then if you check the H and I, they were 0.11 molar, whereas before they were 0.107. So there's a small deviation if you have some of the products already present. Let's do another example. The H2 is this small number, the I2 is this small number, and the HI is slightly bigger, and we don't know if it's big enough. So we have to figure out which way the reaction will shift. The way that I did that was I did products over reactants, so 0.0224 squared, divide by 0.004 and 0.006, and found the Q is 19.5. So this is just products over reactants, and that means it's product favored, but is it product favored enough? Remember the Kc was 54.3, so we need to make even more products. So again, the shift is to the right. We just sum everything out for the equilibrium. We have harder numbers to work with, so you'll notice HI is squared, and the H and the I are different. So in this case, what we're going to have to do is a crazy FOIL and quadratic formula in order to solve it. Or, and I don't show this on here, but you can actually negate, like take out this minus x, because we know that the shift is not going to be that much. The Q is 19 right now, it only has to get to 54. So what we could do is cancel out these and then just cross multiply 54.3 by 0.0623 and 0.00414, subtract out the 0.0224, divide by 2 and square root. So it's a little easier than foiling. So you can only use this minus x approximation. Don't take off the plus 2x, that's more important. These little tiny minus x's, if you know the shift will be small, because it's only one x, not two x's, and you can't use a square root rule because the x squared and the I squared are not the same. So we're going to be practicing when we can use which approximation. At the end of the day, I got these values, which shows that HI went up a little bit from where it was, and the H2 and I2 went down a little bit from where they were at equilibrium. That way they can be the same ratio as K normally is. So back to the question of the video. If the phosgene gas is a highly toxic nerve gas in World War II, and they gave the Kc, and an experimental chemist studies a sample of polluted air that had these concentrations of the gases, which way will it proceed? So we can calculate a Q, which is products over reactants. We'll plug our numbers in, which would be 1 divided by 1 times 0.25, and we'll get a Q of 0.4. we'll compare that to the Kc value and say that's much higher than the Kc value, and therefore the reaction has to provide a reverse reaction to decrease the abundance of phosgene, which in one respect might be great because you'll have less phosgene in the air. It's showing that eventually the phosgene will get to a point where it's a lot less and maybe not as toxic. However, notice that the reaction will form carbon monoxide instead, and so I don't know how much better that's going to be. What will the equilibrium concentrations be? If they actually asked you for the equilibrium and you were given initial, you would have to do a ice box. So I plug the numbers into ice. I know that the change will be towards the products towards the reactants as we just said, and there was only one of each chemical. So I'm going to take away from the products and add to the reactants in a 1-to-1 ratio and solve for the equilibrium. I'm going to plug that back into my K. So the products, which were 1 minus x, and the reactants 1 plus x and 2.5 plus x. I'm going to solve for x by boiling or by an approximation rule. So in this case, I would still do the plus x approximation rule probably, since x is going to be small since the K is very small. And then I'll resolve for the x that was in the initial part. And when I do that, oops, I didn't mean to do that. I get an x value of 3 times 10 to the minus 3. What that means is if we add that to the values, the phosgene will go down only a small amount, whereas the CO and the Cl2 will go up only a small amount. So it actually doesn't shift as much as we had hoped. This was an initial change equilibrium because you were given initial and you wanted equilibrium. At this point, you should be able to use reaction quotients to figure out which way the reaction will shift, and ice boxes to figure out exactly how much you'll have at equilibrium.